I'm standing in Los Trancos Open Space Preserve, and this line of markers marks the trace of the San Andreas Fault. And back in 1906, if I'd been standing here, I would have seen this hill move this way about 3 feet in a heartbeat.
The 1906 San Francisco earthquake toppled buildings and sparked fires that raged for 3 days. 3,000 would die. Then, in 1989, came Loma Prieta, a magnitude 6.9 earthquake that also broke on the San Andreas Fault. Today, top scientists are digging up new clues about earthquake behavior. How close are they to being able to predict the next big one? Can scientific discovery outwit seismic certainty?
Now, as we look to the next 30 years in the San Francisco Bay Area, we believe the odds are about 62% that there will be an earthquake of Loma Prieta size or slightly smaller, magnitude 6.7, sometime in that 30-year time frame. We can't say which fault it will occur on, but we can identify the faults that are most dangerous.
The Bay Area sits atop the boundary between the North American and Pacific plates, which are constantly grinding past each other. The strain from the movement builds up along faults or cracks in the Earth's crust. When the strain becomes too great, the fault slips, releasing energy in the form of seismic waves, which produce the shaking we experience in an earthquake.
We have nucleation events, in other words, beginnings of earthquakes that happen all of the time. And we need to understand why one little beginning of an earthquake runs away to produce a big one. That's the big challenge that seismologists are facing.
So to answer this big question, scientists are thinking small earthquakes, that is, which originate miles below the Earth's surface.
Our challenges are a little bit like what it would be to do astronomy in a coal mine. First thing the astronomer might want to do is drill a hole to the surface and put a telescope up there, and that's essentially what we're doing at SAFOD. We're getting that first look inside the earthquake engine.
SAFOD, or the San Andreas Fault Observatory at depth, is an experiment funded by the National Science Foundation.
We're actually trying to drill into an active fault that regularly produces very small earthquakes, but nonetheless earthquakes that are big enough to teach us about how earthquakes work. And we're going to be making the measurements under the conditions under which those earthquakes occur. We're going to exhume the material, the two sides of the fault that produce that earthquake, and we are going to monitor that earthquake with instruments that are right up next to the fault, watching what happens as these earthquakes occur.
SAFOD is located in Parkfield, 95 miles south of Monterey. Since 1857, earthquakes have been recorded there with surprising regularity.
By having identified one of these areas where these small earthquakes recur very regularly on exactly the same part of the fault and produce exactly the same earthquake over and over again, it's almost like a natural earthquake machine. We will be able to watch the earthquake nucleation process many, many times in the future with different kinds of instruments, and eventually have a fairly complete understanding of what happens in a fault zone as an earthquake is about to happen.
The SAFOD team drilled 2 miles below the Earth's surface to place seismometers directly inside the fault zone. These sensitive instruments measure seismic activity around the clock.
The earthquakes we're studying, these small earthquakes, bridge the gap between those laboratory and theoretical studies and the real Earth. We can actually determine how applicable those laboratory tests are, the theories based upon those tests, to real earthquakes that occur on the San Andreas Fault. And once we've confirmed those theories, we can then scale them up and apply them with confidence to even larger faults and the kinds of earthquakes that pose danger to the public.
But what the public really wants to know is if studying small earthquakes at their source reveals how to predict larger, more damaging ones.
Perhaps our monitoring instrumentation will detect changes within the fault zone that tells us that an earthquake is coming. That would be truly wonderful. But even more basic than that, earthquake prediction is based on ideas about what happens inside a fault. And we have very little direct knowledge of what happens inside a fault. And that's why the question of whether or not earthquakes are predictable is so difficult to answer.
For the first time, the SAFOD team has succeeded in extracting core samples from the San Andreas Fault. Just 8 hours ago, this sample was buried deep underground. Now, it's being studied to learn how seismic activity helped shape its rocky DNA through millions of years of earthquakes, great and small. As the SAFOD team goes deep to investigate the San Andreas Fault, Roland Bergman takes a bird's-eye view of another fault closer to major cities.
We're up at the Berkeley Stadium right next to the Hayward Fault. In fact, only 6 feet away. This is about as close to the fault that we do our GPS measurements, where we measure motions related to this faulting. So this is part of our GPS network.
The Hayward Fault runs nearly 50 miles under densely populated areas. It moves or creeps millimeters every year. This releases a little bit of strain, but eventually it will snap.
So the Hayward Fault is one of the 2 major faults in the Bay Area, the San Andreas being maybe the more famous one. The Hayward Fault had a big earthquake in 1868, and it's known to have earthquakes every 150 years or so. And so having had one 140 years ago means we're really due for another event on the Hayward Fault.
But exactly when is anyone's guess. There's no way, at least yet, to give accurate warnings days or even weeks in advance. But if you ask Richard Allen, even a few seconds can prove vital to saving lives and protecting infrastructure.
EALARM stands for Earthquake Alarm Systems. Well, the idea is to offer some kind of short-term warning. We already can come up with forecasts of earthquakes. That's the probability of earthquakes over long periods of time, tens of years. And of course, we have rapid response. We rapidly get earthquake information in order to get emergency crews out to respond to an earthquake. So the idea is, can we do something in between? And that's what earthquake early warning is about.
EALARMS uses a network of digital seismometers. They communicate information seconds after an earthquake hits, but before it rips through the surface and does damage.
Well, so 10 seconds doesn't seem like a lot of time, but there are actually many applications that we can make use of. For example, transportation systems, we can start to slow and stop trains. The BART system could start to slow its trains. Airports could stop planes from landing and taxiing. And so by taking all of these approaches, we can reduce the overall impact of the earthquake and have us a safer community.
In a kind of earthquake forensics, a real-time simulation of the 1906 earthquake reveals the anatomy of seismic waves.
You can see as the rupture emanates the P waves, which is the yellow circle, and the S waves, which is the red circle, emanating from the fault. And the P waves, they travel fastest, so they arrive first, but they have very little energy associated with them, so they don't do much damage. The S waves travel more slowly. They arrive at the surface later, but they have most energy, so they're what's responsible for damage during an earthquake. So by detecting these P waves that come first, we can assess the hazard posed by the earthquake. And we can issue a warning to people before the S energy arrives, which does all the damage.
The amount of warning time you'd receive depends on where you are during an earthquake.
So if we were to have an earthquake on the Hayward Fault, so let's say it initiates up to the northern end of the Hayward Fault, then over in San Francisco you would probably have 4, 5, perhaps 6 seconds of warning, whereas down in San Jose you would have 10, perhaps 15 seconds of warning.
EALARMS is still being tested in the lab. What remains to be resolved is the cost of rolling out the system and how best to communicate the warnings to the public and first responders.
And by the time we're ready to have this warning system running, which will be 5 to 10 years from now, we'll have much better communication systems. And so potentially the equivalent of your cell phone could receive this information, and then it could warn you of the ground shaking you expect at your particular location.
It may seem like a small step forward, but in the face of the inevitable, every little bit helps.
Every time there's an earthquake, we still learn a great deal. We have to always be looking for new ways to use this information, new ways to use the technology around us in order to mitigate these future earthquakes. Because there will be surprises, there's no question about that. There will be surprises in terms of future earthquakes.